Gonna record and share my screen. Where's that? Alrighty, and then I'm gonna get my participants just in case all of a sudden someone shows up. There we are. And our chat, just in case you chat me something. All right. So we're going to do our 4-5 assignment. And you're the only one here, Glenn, but either way, if you want to write as I'm going, you can show as much work or as little as possible or something, and then you can show it to me at the end and you'll get the points right away. All right. Anyway, it's fun. All right. So here we are with 4-5. Okay, so this is when we were doing the not inverse, the flip fractions of these. So it looks like we are looking at a graph of one period of cosecant x and 2 cosecant x are shown. So of course the only difference between one and the other is the fact that there's that 2 there. So what they want you to do is identify the graph. So we've got a y1 and a y2. And again, the only difference is that one of them is more vertically stretched. And so the only one that's more vertically stretched or actually horizontally narrow is going to be y1. How nice that I used that for for that color. And then the next one is going to have to be the cosecant or the parent function. So y2 is cosecant and 2 cosecant is y1. That's all we're doing, identifying. Well, can you slide it over here and then I'll help you? Oh, it's upside down. Okay. So moving on, the graphs of 2 periods of 0.5 tangent x. So again, this thing is a vertical, vertical compression because it's 0.5. Which of course is the same as the horizontal. Oh yeah, I see, it's done. The video we were watching is done. Okay, so moving on. Vertical compression of 0.5 or horizontally stretching. Ooh, definitely this blue one here looks actually a lot more like it is stretching out because potentially this would be happening here, but this is a lot wider. So in that case, we're going to have y2 as the vertical compressed one and then y1 as 5 tangent. So this is vertically stretched. And so that's going to be y2, or sorry, y1. What's up, hon? You don't want that show anymore? Yeah, well, that's the only show we have on there. All right. So then we'll do the next ones. Cosecant x and 3 cosecant 2x. Okay, well, your show is out in the living room if you would like to go do it. We're having a nap time situation soon. Well, we don't have that one. So cosecant, the original one is on here, and then 3 cosecant 2x. Geez. Okay, so this is vertically stretching from the 3, and then it's also, in this case, horizontally compressing. Well, let me think about it. Horizontal, yeah, compression. And so let's see which one is which. I don't actually have a good sense of which is which, so let's see. Vertical stretch, which would mean it's horizontally compressed. Oh, so that's gonna be this one. So y1 is this one, and then y2 is gonna have to be this one of the original. Because if we're vertically stretching, it's gonna get skinnier. If we're horizontally compressing, it's gonna get skinnier. And so that's what's happening there. Hey, Mom, can you come get Logan? She's not going to hear me. Okay. So then we have cotangent, which is just regular. And then this one here, whoa, which does this thing, which is moves it right a half. And this one, which moves it up 3. So right a half and up 3. Well, the only one that's not on 0 or on the axis is this one. So the red one must be y1, and the blue one must be cotangent of x. I don't know if you mean f like what the f, or if you accidentally typed f. So if you have a question, you should let me know. F in the chat. Okay. All right. So moving on, we're going to move on to our next one here. So we've got to describe the graph of the function in terms of a basic trig function. So basically, what does it mean that it's doing to the 2? What is that 2 doing? And so that just means it's horizontally compressing it. Yep, by a factor of 2, not that that's a huge thing. And so now we're going to graph it based on what we see. So let's see, tangent. I just want to make sure I get it right. Gotta go to a different mode. Yeah. All right, so tangent, let's see, goes up and to the right. So I just want to double check that. So tangent is going to go through that way, but then this 2 horizontally compresses it, and also therefore then changes its period. So I am going to go ahead and, all right. So we also know that our period changes because our period is supposed to be involved in this b here. So our period is supposed to be 2 pi over the b. And so our period is now going to be 2 pi over 2, which just means that it's going to repeat every pi. So on that note, I'm going to erase this piece. That was just to reference. All right. So on that one, we are doing tangent, which normally would go through the axis here, and it looks like it would go out to a repetition of, 1 second, window. So it looks like it takes pi to repeat, but of course, a repetition would be 2 of those. So let's see, we're going to have a vertical, oh, here, I'll do it with this. We're going to have an asymptote potentially here. Sorry, potentially here and here. But we want 2 of them, so we're going to have 2 of them in this area. Graphing is not an exact science here. So it's going to be something like that, but then that would have been the original one, and now we want it to be, instead of 2 pi, it's going to be pi. So that means I'm going to squish this into half of the area that it used to be in. All right, and so now we're going to have our tangent little segments going through and through again. And they are supposed to be at these exact points here, but of course, that's how that goes. Does it say it wants 2 periods of the function? Okay, so let's keep going. Yeah, so whoops, I want this. No, didn't really want that, wanted that. There we go. And then another one. All right, so this is going to be 2 periods long. Because pi is one of the periods. Now, just to check, because of course graphing by hand is ridiculous at this point, we're going to go to Desmos and just get a better view of what's happening with this graph. So we want tangent and then tangent of 2x. Oh, that is hard to look at. So Let's go to -2 pi to 2 pi, because that's what my
It's like
grid has. What?
modern art.
Yeah, it is. It is. Totally is. That's what I was going for. 3 to, no, -3 to 3. How about? Okay. So that's a little better, maybe. Okay, so this is what it was supposed to look like, potentially going through 0, 0. Did I do that? No, I seem to have shifted it over a little bit too much. So I don't have the piece. Oh, here. What can I do? I'm so clever with the computer now. All right, it's supposed to be like that. All right, took a little snapshot, and it's right here. Is that it? No. Okay, so by saying I'm clever, I'm not at this exact moment. Let's see, where did my picture go? Went over here. Yeah, I'm probably making you dizzy. All right, so taking a look at what Desmos says, we should have gone through the origin. So I should take all of this and move it over. There we go. Otherwise, it is the same thing. Yay! Okay, so that made me feel better. All right, so we just need to understand why we needed to know that it went through the origin, and tangent goes through the origin. So I should have just taken one of them instead of halved it. So anyway, we'll do better on the next one. That sounds good. Cotangent. Oh man, exciting. Okay. So just for reference on cotangent, I wonder if yeah, they do cotangent. We're looking at basically the reciprocal of tangent. It looks like it goes through pi over 2 when it's regular. But right now we want to do a flip of it because it's got a negative here. And then we also want to horizontally compress it by a factor of 3, which just means we're going to change the period. So our new period is going to be 2 pi over b. And in this case, b is 3. And so we're going to do 2 pi over 3 to be 1 period. And we're also going to go negative. So just as a reference, again, cotangent would potentially have an asymptote at 0. So we're going to still have that asymptote at 0. Yep, so asymptote at 0, but then our next asymptote is going to come at 2 pi over 3, because that is where our period says it is. So let's see, 2 pi divided into 3 is not really in here nicely. So it's about here. 2/3 of the way to 2 pi. Or, yeah, 2/3 of the way to 2 pi. Let me think about that for a second. Because pi, and we want 2/3 of pi. Yeah. Okay. So then if that's our period, we're going to have normally the graph would be going through here at pi over 2, but we've, let me see where 3 pi over 2 is. Oh. All right, so let's just look at it here. So here's where 2 pi over 3 is. Why is that over there? Oh, it's a different scale than what we have here. All right. Can I do as a coordinate? Okay, there's 2 pi. All right, so 2 pi over 3, 4 pi over 3. Oh, so 2 pi over 3 should just be right here. 2/3 of the way. It's very hard to divide this into 3 pieces. No, it's this one. Okay. Yikes. So again, normally it would be going down and to the right here, but we're doing a negative, so it's going to end up flipping, right? And then we have this 3 that's here, so it's going to end up, again, squishing it a little bit more. So now we have 1 whole or 2 whole between 2 pi, 2 whole repetitions of this. Because with tangent, it's weird because it feels like it's not, it feels like only one of these is a period, but actually two of them for tangent and cotangent are a period. So you gotta have two of your little guys going through here within one period. Where is my, there. All right, and just for reference again, yeah. So we're gonna make them both go like this, shoop, which makes it seem very much like it's tangent, but again, it was inverted, so, or made negative, so it's gonna look like tangent again. Wow, straight lines is hard. All right. So then to make two periods of that, we would do that. Yay for the glory of computers. All right. So that's exciting. Wow, lots of fun stuff. Basically making sure that every time you do this, you know where those asymptotes are. All right, now we have secant of 3x. So again, we want to find out what our period is. So our period is going to be 2 pi over 3 in this case. So just the same one as we did before. And 2 pi over 3, oh, that's why I was having this wrong, because this is a pi. So if I break this into 3 equal pieces, that's kind of here. So this is where 2 pi over 3 is. And then this would be, what, 4 pi over, what's 2/3? Yeah. All right. And so that's where our first period is going to be, which I'm going to do with a skinnier pink line this time. And then potentially here. Let me think about what I'm doing. I think it would probably be easier if I did this in degrees, but hey, look at me go. Okay. All right, so it is what I was thinking, which was 1/3 of the way down. So if I break this entire thing into 3 parts, right, because this is 2 pi, yeah. So 1/3 of the way is kind of here. Nope, it's a little bit more right there. So we're going to make these our asymptotes. All right, and then secant, if you remember back to the notes, is doing cosine. So where it comes up at the axis and back down. All right, it's going to do cosine, but then each of these loops, because secant is actually what it meets at, is going to meet at that axis up here. So we're going to end up with kind of these upside down or right side up parabolas. All right, and so if we graph sine with 3x, again, our period is 2 pi over 3. Oh, sorry, cosine. We're at cosine. So where's 1? We'll just say this is 1. And we need to do an entire period by the time we get up to here. So, and down to the middle. So we got to go in, down to the middle, and back up. And so our secant is going to be the fact that at 0, it would have an asymptote. So it's going to go here. And then it's going to meet here and here. And so that's just the period. It's not actually the asymptote. And then here. And so, of course, it would repeat a little bit. So if I take the time to make the rest of cosine, it's going to go back in here, down, and up again. So these were my period lines, so sorry about. Now we'll make this. And so if we want to make our actual asymptote line, that's going to be where cosine is at 0. So that's going to be right here, right here. And oh, I didn't draw the rest of it yet. All right, and so yeah, I can copy that. So our other asymptote would be there and there. Wow, this is like so exciting. Okay, so that's that. And then our next one is going to be cosecant, which comes from sine. So we would want to graph sine of 2x, meaning that our period is going to be 2 pi over 2, or just pi. And so we're saying that sine, which would generally start at 0, 0, and go up and down and around by 2 pi, is now going to do it by pi. So that means that we're going to go up to here, back down, and up. And so that's going to be sine. We're doing 2 of them, so I may as well draw the next one as well. So that's sine, but then cosecant is going to end up having, just like this, the opposite, where it hits it at its maximums. So right here, it's going to go up, and then of course at a sine of 0, it's going to end up being divided by 0, so it's going to have an asymptote. Then it's going to meet here. And here again. Just not the best with a period that has 3 on the bottom. Just saying. Oop, oop. Oh, that was quick. Should go very much through this point right here. All right. And so we're looking for the red equation. The blue, again, as fun as it is actually not part of the equation. So if you just graphed it the way it is, without that in there, this is the image of the graph. But of course, I have this here for reference so that you can graph it nicely. So anyway. All right. Next one, because of course we have, oh my gosh, 4 more. Great. Let's see. We have another period again that has changed. It's always a good thing to identify. So our period ends up being 2 pi over 2. And so it's pi again. We're doing tangent, 1 over tangent, so cotangent. And then it's also stretched vertically. So it's kind of hard to do on a grid by hand, but that just means that if it had kind of this snake-like idea, it would be just skinnier as it has the snake. So just more compressed. So stretched by a factor of 2, we're kind of doubling. All right, so when it comes to cotangent, probably the best thing to do is have a reference for it, which we have here. All right, so just for reference, here's our tan and our cotangent. All right, so tangent goes through at the origin, but cotangent, because this has a 0 at the origin, now has its asymptote at the origin. So if we draw our asymptote at the origin, because that's where tangent would have hit it, and we also know that our period is pi. So taking a look at, oh, there it is. Taking a look at where pi would be. All right, you go take care of your chickens. All right, so here's our pi and our cotangent. Potentially 1 or 2 of these would exist between 0 and 2 pi, but now it's just going to be one of them that exists between 0 and, or sorry, 2 that exist between 0 and 2 pi. So that means that we're going to have this and this. And again, tangent would have normally gone up and to the right, but cotangent is going to go down and to the left. And of course, enter at that origin here. So we're going to go down and to the left. And that was kind of perfect, so I'm just going to copy that one. All right, and so that is one period because it has two of these things within one period. And so we do want to copy that and paste it for a second period because it wants 2 periods worth of graphing. There. All right. So then the next one, oh, gross, is going to be, let's see, a period of 2 pi over a half, because our b value is a half. So that actually means that our period is 4 pi. So that means that on this entire thing here, we're going to have 2 of those little snake things because it's doubled its size. We just talked about tangent, how it goes through the axis here. So we're actually going to have one of them and then kind of a half of one here and then the other half of one here as we graph this. So it's going to kind of look like that. It also says that it's 3, which just means that it's going to have a taller, it's going to be stretched, but of course that's very hard to do on by hand, is showing how it's stretched. So let's see, normally there's our axis and here's our other one. So I kind of do that freehand nice. So here's our tangent, and here's our other tangent, and then this piece here. Because of course, in order to fit 2 periods on, we kind of have to have a half of a period over here and half of it over here. All right, or half of the image, because it's not a period, this whole thing is. All right. So there we go. And then it does say graph 2 of them, but we can only literally fit 1 on here, so sorry. I'm sure you're all upset about that. Alrighty. So moving on, oh my gosh, so much graphing. The next one is cosecant, which comes from sine. So if we focus on sine and the fact that the period is going to be 2 pi over a half, that means that we're going to have 4 pi as one of the periods of sine. So yikes. So from here to here, we're going to have an entire sine. It is going to go to 1 and down to 1. And it starts here and ends here. It's going to go up at pi and back down, all the way down and back up at pi. Wow, that's really, it's really stretched. Huh. Oh, I just graphed sine completely backwards. I did inverse sine just for fun there. Because of course it goes up at the origin. Hello. So is graphing hard? Yeah, there you go. Good to know. All right. Here we are. All right, I just decided it would be centered there. Okay, so that's our sine, and so if we want cosecant, remember that if it goes through at 0, that means that we're going to have our asymptote there. So we have an asymptote right here because you're going to be dividing by 0, and that's a no-no. And then our actual graph is going to hit up here just as it does with this one, and then go up, and then hit here where this one does, and go down. So again, the blue equation is your graph of cosecant, but the red one is there to be able to actually figure out how to get to that graph. Here we go. All right, and then the last one is going to be secant of 4x. So that means that our period is going to be 2 pi over 4, because our b value is 4. And so we've got pi over 2. So an entire period of cosine is going to happen between 0 and pi over 2. And cosine starts up at 1. In this case, it's actually going to be starting up at 3 because it's stretching vertically. And then it's going to go down to 3 as well. And then back up. So we're going to have this entire thing within a pi over 2. And then since it wants 2 periods, we'll do it again to get up here. So down and through, back down to 3, up and through and up. And so if we want to do secant of that, that's going to mean that I'm going to have this piece here, this piece here, I guess a half of one right here, and another half right here. I'm probably making these a little wider than they should be. Because then your asymptotes is actually technically there. So yeah, I did make these a lot wider than I should have. And here, because again, it's just where sine goes through at 0. So that would be dividing by 0. All right, so this one looks good, but this one is way too fat. So sorry about you. We'll put that one there. And ooh, that one's a lot wider than it should be. Get rid of that guy. All right, and it's supposed to be in here. Okay. So either way, again, taking out this purple part, it is just the red equation that's on there, okay? The purple one is just to give you the basis. All right, so then we go back to domain and range and continuity and all of this analyzing of an equation. So we're going to analyze the cosecant function. Again, the best way of doing this would be with an image. So let's pull up our image. And we want cosecant of x. All right, so if this is cosecant of x, what happens is there are, let's see, a domain. So your domain are your x's, and it looks like it's going to exist between 0 and pi, and then every pi after that. So our domain, and people will write it differently, but basically it's between 0 and x and pi, which I'm just going to type because apparently I don't have that symbol right here. And then it's actually plus every pi after that. And so they do this plus k pi thing to everything, which I should definitely just get a pi symbol because this is going to look ridiculous. Let me write it. All right, so here's my little pi. All right, so that's the idea, is that the domain is going to exist between 0 and pi. So I'm going to put that in red. But then it's also plus a k pi revolution after that. So again, it exists between here and here. And then if you add 0 to and pi, you'll get here and realize that that's also a domain that works. For the range, we don't exist between 0 and -1 or -1 and 0, but everything else exists. So my range is not as complicated because it doesn't have to do with pi's and things. So in that case, our range is between -infinity to infinity. So I'm just going to say, I don't have a symbol, so I'll write it. So we're going to say -infinity to -1, and then also 1 to infinity. That's a fun range. Okay. Then its continuity, it is definitely not continuous, because in order to draw that graph, you are going to have to pick up your pencil, that's for sure. It's increasing, and this is where another one of these k pi things is going to happen. It's increasing starting at, we'll start at 0, from pi over 2 to pi. But then every k pi after that. So if we look at it, we're saying it's increasing from pi over 2 to pi. Oh, and then down here, but then every, I suppose, 2 pi. Yeah, from here to here is 2 pi. So we will stretch this out a little. Let's see if I can do that. Nope. All right, I'll squeeze it in. So plus 2 pi. And then this is going to be plus 2 pi k, k2 pi. And then the other part that it's increasing is going to be not up here, but this one, increasing from pi to 3 pi over 2. So pi to 3 pi over 2 is also increasing, and it's all of the repetitions of that afterwards. And this is actually, so plus 2 pi k, and then plus 2 pi k. And actually it's plus or minus, because you could go backwards and get the negative ones as well. So we'll do plus and minus up here as well. Okay. Then it's decreasing gross between 0 and pi over 2. So 0 and pi over 2. And then we're talking about all of the x's between that. But of course, we have to add and subtract the fact that it repeats every 2 pi. And then this one. And then the next one is, let's see. For decreasing, right here, 3 pi over 2 to 2 pi. And then, of course, every revolution after that. So plus 2 pi k and minus, and then plus and minus 2 pi k here. And I forgot the minus there. Okay. Then our symmetry, let's see, definitely symmetric on these minimums and maximums. So we're going to say at pi over 2. And then every revolution after that, every repeat, that is going to be, what's the distance? Pi between them. So symmetry is at x equals pi over 2, but then every pi distance after that. It is not bounded, because bounded is if it doesn't go up or down for infinity, which it does. So it is not bounded. It's kind of bounded in between, but that's not a thing, so we're not going to identify that. Its extrema are going to be, as we just talked about, at pi over 2 and then 3 pi over 2, because those are our symmetry pieces. So its extrema are pi over 2 and then plus or minus pi after that. So those are all of our values. And then it's either going to be comma plus or minus 1. So it kind of just depends on which x value you're talking about. Our asymptotes are going to be here at pi and then every pi after that. So we're going to have x equals pi and then plus k pi. So it's whatever value of k, pi is after that. And then our end behavior, weirdly enough, does not exist, because that would mean that the end, which it doesn't because it repeats, would end up going towards something. But we're going to write DNE, which actually means does not exist. There are limits that we can do. So we can say the limit as it approaches 0, that's fine, but we can't have a limit as it approaches infinity. It just doesn't exist. So darn. All right. Then we have a bunch of tangent, and then we also have our next piece. And honestly, I am not, oh, I skipped those ones. I'm not going to do this for all of those. So, but of course, you should pick one of them and check the answer key to do that, because I do want you to practice, but P.S., I don't need to practice this one, and you can always use your calculator. So clearly I need to practice graphing, but here we go. So. All right, so the next ones, they want you to describe the transformations. This is kind of what we were doing before, but then also graphing at the same time. So if we're going to describe the transformation, this one means that tangent is going to be stretched vertically and then technically by a factor of 3, but we usually don't necessarily need that whole phrase. And then this one here is going to be flipped or reflected on the x-axis. So instead of having your tangent go up and to the right, it's going to end up going down and to the right. All right, and then for 3 cosecant, that just means it's stretched vertically by a factor of 3 again. And then this one is just going to be stretched vertically by a factor of 2. And of course, you can look at that. So if we take the time to graph this one here with its parent function, which would be tangent, and then this new function, which is 2 tangent, hopefully you can see that as much as it looks pretty much the same, it's going to have the same asymptotes. This one is steeper, and so it has been stretched by that factor of 2. So steeper. That's another way of describing it. And then the last one's here. Let's see, we got a lot of stuff going on. The negative means that it's going to be symmetric on the x-axis. The 3 means that it's going to be stretched vertically. And so we can just abbreviate by 3. And then the half means that the period is now, instead of 2 pi, it's become 2 pi over a half, so 4 pi. There it is. All right. Let's do this. The next one, symmetric on the x-axis because this negative, yep. Stretched vertically this time by a factor of 2. And then actually it's the same period because it's got a negative out there. So let's see. Sorry, it's got a half out there, just as this one did. The last one got a little bit cut off. This is supposed to be a 2 here, but it looks kind of like a freaky 7. So either way, the next one is symmetric on the x-axis again, so it's flipped. And then let's see, pi over 2 is our period. So we've got 2 pi over 2. So algebraically, let's see. Our period for this one is 2 pi over b, and our b in this case is pi over 2. So that means that we have 2 pi times 2 over pi. And so these pi's will cancel, and so we just have 4, actually. So there was a 4 there, and now there's not. And it's not vertically stretched, but it is shifted up 2 units. So now instead of having the 0, 0, the x-axis be kind of the place of reflection, it's now going to be up at 2. And then this last one, wow, that's kind of a lot of things happening. Did it again. This needs to be a 3. So I've been copying and pasting. Okay. And then this one's oh good, not symmetric anymore because there's no negatives, but it is stretched vertically by a factor of 2. Its period is now 2 pi over pi, and so that just means 2. And then it's also shifted down 2 units, so it doesn't have that x-axis as its middle point. It's got the down 2, -2. All right, so that has been enthralling, and I hope that you understand a little bit more about graphing and a little bit more about your shifts, and then also your analysis, which we've done a lot of, and then this graphing idea. So always good to get your calculator to have the same as what your graph does, because otherwise you end up with something that does not look the same and you're like, wait, what? So always want to make sure, like I was doing on Desmos here, where you can change your scale here. So your x-axis, I usually do -2 pi to 2 pi, and then my step, as you can see in this one, is by pi. Well, actually, it's by pi over 4, just to kind of have it match so that you can see where your pieces can go through. All right, so I'm gonna stop this. Bye.